We now welcome to the stage Cecilia Garraffo, AI astrophysicist at the Smithsonian Astrophysical Observatory and the founder and director of Astro AI and Earth AI Institutes.
Thank you for the invitation. I'm very excited to be here today after such an inspiring morning and first talk in the afternoon. And I'm very excited to be here today to tell you about how we are transforming astronomical discovery with AI. And I need a clicker, I think. Sorry. I'm sorry. Okay, let's see. Okay. So we are at the verge of a data revolution in astronomy. With the next generation observatories coming online soon, we're going to observe more data in 1 year than all our history combined. This, for example, is Vera Rubin, a very powerful telescope that will open its eyes to the universe in less than 1 month. 4th of July is when we expect first light, and we're very excited about it. Vera Rubin alone will detect 10 million astrophysical events per night. 10 million per night. And that's just one of many telescopes coming up soon. One particularly exciting kind of astrophysical phenomena are exoplanets. Exoplanets are planets outside of our solar system, planets that are orbiting a star that is not the sun. And the first of these planets have been discovered in 1991. And since then, we have been finding more and more of them faster each time. Here I'm showing exoplanet detections with time, and you can see how more and more appear, the discoveries accelerate as our telescopes get more powerful. Everywhere we look, there are exoplanets. They're everywhere. And so right now, with more than 5,000 detected and confirmed planets, exoplanets, so planets outside the solar system, the question is, that is a very fast-growing number as well. So the question is, how are we going to know which ones are the really interesting ones, the ones that are worth following up on, observing further? We want to find the ones that can harbor life, whether they're like Earth or nothing like Earth at all. And so we all know that AI is good for big data. But here's what I'm most excited about. With AI, for the first time, we can intentionally look for the unexpected. New patterns, new phenomena hiding at plain sight. New planets that will unveil new kinds of life. Maybe completely unexpected planets that we've never seen before. The problem is that astrophysical data is complex. So the state-of-the-art AI models out there do not work for astrophysics. Astrophysical data is much more complex than just text and data for which these models have been optimized. So we need models that understand this data and that apply the physics that we know while being flexible enough for discovering new physics. Our models must be accurate, must represent reality, and we cannot afford bias or making up stuff that doesn't exist, or hallucinations. So for that, I created Astro AI, the first institute dedicated to AI-driven astrophysical research. In Astro AI, we design and develop our own AI tools and models to answer the most challenging questions in astrophysics. And today, I'm here to tell you about one of our most exciting projects, that is finding life elsewhere in the universe with AI. So we now know that when we look at the night sky, a vast majority of the stars we see in the sky are really planetary systems, like our own solar system. So there are exoplanets orbiting these stars. And the question is, you cannot avoid to ask the question of, are we alone? There's hundreds of billions of stars in the galaxy, hundreds of billions of galaxies in the universe. Are we alone? with already more than 5,000 discovered exoplanets. The very exciting part is now with the new James Webb Space Telescope, we can detect molecules on the surface of these planets, on the atmospheres of these planets. I want to pause there and say how incredible that is. We can look at tiny molecules like water and methane that we would need a powerful microscope to see if we had them right here in front of our eyes. We can now see them on exoplanets that would take us millions of years to reach. And we want to do that because we're looking for biosignatures. Biosignatures are molecules that indicate the presence of life. How do we do that? How do we detect these tiny molecules? So when a planet goes in front of its star, of its host star, James Webb looks at the light from the star that shines through the atmosphere and makes what we call a spectrum. Then we can look into the spectrum and read out the molecules that are present on the planet's atmosphere. How? Because each molecule absorbs some of the light with a different pattern. These are like fingerprints. Now, these are super subtle. These are tiny particles in a tiny atmosphere compared to the size of the star. And the light has traveled years before reaching our detectors. So we have weak signals with a subtle pattern. Traditional methods struggle with this regime. But that's where AI thrives. So the way scientists do this right now without AI is making spectra for each different molecule that you're interested in seeing if it's present on that atmosphere at all different temperatures, all different pressures. You get very quickly to billions of possibilities and then match them to the observed data or spectra. This is not only super slow, but it won't give you the full answer. One molecule at a time doesn't give you the full answer. This is a lot like music. You can listen to a cello, and you can listen to a violin, and you can listen to a trumpet individually. But it isn't until you listen to them all together that you can hear the full symphony. So if we really want to find life, we need to reverse engineer and extract the molecules all together from the spectra. So we did that for months after the inception of AstroAI, and we won this international competition from the European Space Agency for that. So our model extracts these molecules directly from the spectra and gives us not only the presence or absence of the molecules, not only that answer, but the abundances, how much of each of them is in the atmosphere, the temperature of the atmosphere, and the pressure of the atmosphere. This model can tell us from the light that we observe with James Webb Space Telescope whether a planet is likely to host life or not. No, that is life as we know it. We build this model with molecules that are biosignatures on Earth. We know them because they are biosignatures on Earth, and they are in the range that James Webb could detect them. And so the worldwide search for life elsewhere in the universe is focused on these 5 molecules. But we want to go beyond life as we know it. What about other forms of life? There's so much variety of life, of planets out there. The variety of planets out there is such that most likely the variety of life forms is gonna be huge as well. And we want to go beyond life as we know it, especially now that we know that there are 14,000 molecules that would indicate the presence of life if we see them. And not only the few we know from Earth. So we are now scaling our model to be able to extract these 14,000 molecules rather than 5 directly from the spectra, the abundances, the temperatures, and the pressures. And this would not only change dramatically the chances of finding life elsewhere in the universe. Instead of looking for 1 out of 5, we're going to look for any one of 14,000. But it also means that we can now detect life as we know it, but also life on planets that are nothing like Earth at all. And finally, and perhaps most importantly, the same AI technology that we develop to look at the sky and to look for life elsewhere in the universe can help us protect life here on Earth. The observations of the Earth atmosphere, this is showing you the data that we deal with the Earth atmosphere, is very similar and share the same data complexity challenges that the astronomical observations do. This is scientific data, a lot of spectra. And so for these methods is where, for this data is where standard AI struggle. But the Astro AI models that we built precisely to overcome those challenges apply to Earth. And so at the Center for Astrophysics, Harvard and Smithsonian, which is the home institute of Astro AI, we not only build and launch rockets and satellites to observe the universe, but we also build and launch satellites to observe the Earth atmosphere. At our sister institute, Earth AI, we're working with these data sets and with these science teams from Tempon Methane Sat to understand better the Earth atmosphere, to identify pollution, to track methane leaks, and to better understand the health of our atmosphere. So the same technology that we use to look for life elsewhere in the universe and protecting our planet are connected by this science-driven AI technology. And I'm hopeful that that perspective will give us a new perspective on who we are, our place in the universe, and hopefully our shared futures. So thank you.
We now welcome to the stage Dan Hammer, co-founder of LGND.
I honestly couldn't have planned this transition better myself. Someone at Aspen knows what they're doing here. So going from exoplanets to our planet, our home planet, everything and everyone that I love is on our home planet, Earth, and I think that's probably true for most of us. Despite its importance, we really don't know precisely how it's changing, and certainly not at a resolution or immediacy to do, or to feel empowered to do much about it. And so, in the next 6 minutes, I'm going to talk about two things. I'm going to talk first about the status of our maps and how they're insufficient, and second, how new AI models and compute can help bridge that gap. All right, here we go. So we launched our AI for Earth project a few months ago at the MIT Media Lab in Cambridge on the Charles River. The amount of information that we have on roads and buildings, especially in the US, is just staggering. These renderings and the fact that they're open to everybody right now via like Google Earth, it's just incredible. And most of us use this data on a daily basis. I mean, I open up Google Maps when I'm trying to go to my local bagel shop at this point, and I do that like hundreds of times. I've become dependent on this information, and it's incredibly good for certain things, but this view is pretty limited. This is a static image that I can reliably navigate, but I can't query or access the information around the context of this image. So much of it is lost through space and time, just because we don't have the way in which to index this image for search, these repeated images for search. So in order to get to the to get to the Media Lab, I walked through Hockfield Court, named for Susan Hockfield. It was a beautiful space. It was probably renovated recently, and I wondered, when was this renovated? Or what was here before? Were there other green spaces built nearby at the same time? You know, was this part of some sort of campus-wide renewal? These were small queries, none of which was especially significant in isolation, but together they create a fluency with what's happening to the places that mean something to me, with local context and relevance. But I just can't access that information, even though it exists. These images are taken, we have thousands of satellites taking images every day of the Earth, trillions of pixels, every minute, every second of every day. It just hasn't been indexed for search in a way that I can actually access it. This is a time series of Hockfield Court between 2007 and 2012. And so you can see that the information that I asked is like, when was this renovated, has already been collected. It was collected incidentally, mainly funded by US military revenue in order to build this technology, but it's there for us. It's just not available for us to be able to type into our search bar, just like we would type into our search bar, please find me the nearest Starbucks. But it's there, and it's accessible if we can index it. The issue really is about the velocity of information and the volume of information. There's too much friction here. Like, it would take a research project in order to be able to identify this particular question, and that the juice just isn't worth the squeeze for these small queries, but they aggregate up into something more. It's reminiscent of an interview in 1995 where Letterman questioned Bill Gates about the value of the internet because we already had radios. He just responded, it really is the velocity and the volume of information that changes the world order. And this is what AI solves right now. It finds the semantic information, the human readable patterns, and otherwise esoteric and voluminous data sources. This is a useful illustration. This is Alabama. Each point represents a patch of satellite imagery on the Earth's surface. In AI parlance, it's a token, analogous to a word or a sentence in an LLM. It's the input to a large AI model for inference and also for training. These tokens are made of dozens of measurements, which can be rendered into RGB, something that we can understand. We've been in an airplane and looked down, and if we understand the Earth and these patches. But there's a lot more information that goes into or measurements that go into the collection of this data. So now they're colored by land cover. This is a label, right? This is red is cities, green is forests, blue is water, orange is crops, and they're still organized geographically, and each one of those patches is associated with what's known as an embedding. This is the output of taking one of those patches in a very large Earth observation model, which is, in this particular case, the P and the T of GPT, a pre-trained transformer, and it spits out a vector. It's a sequence of numbers that contains, without losing much information, most of the semantics inside of that patch right now. And this is very, very similar to the way in which language models work, parallel. About 2 years ago, my co-founder and I started to train a very large AI model on satellite imagery called Clay. And we've been running it ever since. And so now the question is can we reorganize this space, this image, based off of its semantic closeness rather than its spatial closeness? Each point is still organized if it's near each other on this image, if it's near as the crow flies. Yeah, so now suppose we reorganize the points based on the embeddings. We take that long vector and we squish it down into two space, and so now points are close together if they are close together in semantic or concept space rather than geographic space. This was not trained. It was not supervised. This is one of those very large transformer models, and already we start to see clustering of similar concepts. Waters near each other. Cities, the red patch is near each other. And notably, this cluster here are all the concentrated animal feeding operations in Alabama. The size of the cluster is the answer to someone's question, like how many concentrated animal feeding operations are there in Alabama? Or how many were built in the last 3 months? And it's crazy that we don't already know this. This is how we utilize our own Earth's surface. We don't know some basic questions about who's building what where, especially for methane sat in the previous example, to understand where these animals are farting. In order to get that answer right now would require a handcrafted custom convolutional neural net on satellite imagery, data scientists, lots of people in the middle in order to send and receive radio signals, basically. Whereas when we train one of these very large models and make those output embeddings available to everyone, the velocity just increases dramatically. There are already thousands of these early applications of the Clay model. One of them, which uncovered illegal gold mining activity in the Amazon, won the Shining Light Award from the Global Investigative Journalism Network. And the awards committee had said that the story is taking us to where journalism is going. And it was a task so immense that they used AI to crack the code of a story that we would not have otherwise seen. We're rapidly heading toward a world where not just a patient, diligent journalist, but someone like me, an impatient consumer, can investigate and explore and understand the Earth with a fluency that we just haven't seen before. There's so many gaps in our maps, like nature is just represented as the blue and the green blobs in Google Maps. And we don't have any time context or spatial context in that same way, but it's coming. Over the past 15 years, I've built or co-founded dozens of these applications, including Global Forest Watch to track deforestation from satellite imagery, or Global Plastics Watch to measure plastic waste, or Amazon Mining Watch to monitor mining in the Amazon. But these are just a sample. Some of these applications, though, cost like millions of dollars to produce. The more recent ones cost less than $100,000, but it's still expensive. There's friction involved, and the advent of these large Earth observation models is just dropping the cost almost to $0 in some cases to produce data that is locally relevant. Actually, Ben Buchanan at the start of the forum talked about individual agency afforded by AI, where individuals can create things like films which normally required a big team and a big budget. And this really hit home for me because the idea here is that individuals can create these data sets which were normally the domain of federal agencies, military agencies, that individuals, even children, high school students, as we've seen a number of times in applications, can find things and uncover patterns on the Earth's surface that they couldn't find before. Because actually one of our investors started Pokemon Go. If they can find Pikachu in Playground, like, they can find lots illegal mines in Amazon. But I like this vision of a shared future where we know much more about our Earth at a resolution and scope that's commensurate with local decision making, not just for the military intelligence community, but for everyone. It's complicated and it's stressful, not just building the technology or models, but the organizations and institutions to deliver the tech in a way that we would want to see it show up in the world. It's not just research grants or philanthropy. We've needed to go to venture capital and even debt financing, and it just changes the way in which we interact with this information. So I'm getting gray as a result, but it's worth it because this place is worth it. Thanks.
Now, please welcome Cecilia Garraffo back to the stage, and welcome Anup Kaphle, Editor-in-Chief of Rest of World, to moderate a panel discussion.
Dan, thank you so much for that presentation. There was so much knowledge in about 20 minutes. I don't think a ChatGPT could have helped because we wouldn't know what prompt to ask. Cecilia, I want to ask you first. Earlier when we were discussing about this panel, you mentioned that we're able to chat with the universe in its native language. Was that real? What do you mean by chat with the universe in its native language?
Well, it's quite, quite literal. So the way we do that is we add a language model to the models I have been describing that are physical and mathematical. So you have a robust model for the data and to do data analysis that gives you answers with uncertainties and that we can calibrate. And then we align, that's how we call it, but you can think about it as plugging in a language model like the ones we know, pre-trained and retrained on scientific data that is relevant. And so now we can use language to interact with the data and get robust answers and scientific answers out of them. So I think that's, you get rid of hallucinations and you get a trustworthy physical LLM.
Very cool. And you talked about the James Webb Space Telescope. Are there other telescopes that provide this kind of information?
Yes, absolutely. Yeah. So James Webb Space Telescope gives us this detailed spectral information of the atmosphere of exoplanets. But there's other telescopes like Hubble and Chandra and TESS, the Transiting Exoplanet Survey, many other telescopes that are important to give us other pieces of this puzzle, right? Some give us information about the star and how the environment around that star might be more or less friendly for the planet. Some give us information about the size of the planet and their distance to the host star. So these are all different pieces to a puzzle that we need to build to fully understand habitability and exoplanets and hopefully find life.
Yeah. And Dan, in the day-to-day work that you do, how is AI fundamentally changing the kind of questions we ask about life, whether it's about life on Earth or looking for life elsewhere?
So previously in building these like large derived data sets from Earth observation, you'd get one shot. So you'd produce a data set of like where deep forests are in the world right now. And it was very difficult to change or fine tune quality assurance and quality control. It was, the issue was like you got one shot. It was available everywhere, but it's sort of useful nowhere because every pixel was wrong. right? It just doesn't have the local precision. All those errors would aggregate up into, so that you could get a pretty good general stock take of what's going on. But if you were a particular farmer, or you were the steward of a conservation concession, for example, you just don't trust that data. It's not refined enough or precise enough through space and through time to actually make a local decision on. And that's what we're seeing with, if you can have the capability of asking sort of local questions and fine-tuning it just locally. Because if you're a conservation specialist in Brazil, you don't really care if the model works okay in Bangladesh, right? And so the idea here of having much more fluency with what's happening locally, without having to train a gigantic model, but take advantage of these pre-trained models that are out there, the idea of being able to use this modality specifically for local decision-making just hasn't been possible before.
Yeah. And just to follow up, like the kind of discoveries we've talked about here in the last 15 minutes or so, discoveries on the universe or even here on Earth, these could take centuries to actually impact our daily lives. So how does AI actually help compress those timelines?
Yeah, I don't think that there's going to be like one big discovery about like Earth, well, from my domain of like, there's not like, we're not going to, as a result of this technology, you won't, cure cancer. There won't be a particular threshold that you can exceed. It's the accumulation of just much more fluency with the data, being able to ask these triangulating small questions. Like, for example, I'm going to know that this works when I can go, into ChatGPT and ask, when was my local playground last renovated? Like, that information exists and it should be accessible through these interfaces, and it's not, because the Earth observation hasn't been indexed for search. We don't have the infrastructure to serve up these geo-embeddings to sort of AI-first applications. And that's not a breakthrough question, right? That's not but it's indicative of the type of small questions that together change the way we interact with our Earth surface.
Thank you. Cecilia, you talked about the multimodal AI models, right? And can you talk a little bit about how they overcome the limitations of the traditional analysis?
Yes. So
that's taking place?
By multimodal models, I mean in regular language would be different types of data. For example, one type of data is text, one type of data are images, other type of data are spectra for us in science. And so the way we have done astronomy so far has been having scientists specialize on one particular kind of observations. For example, that depends on the energy of the detector they're working with. There's X-ray astronomers, there's infrared astronomers in each one, because you need quite a bit of training to be able to make any progress in each of them. And so the way we typically do this is there's the X-ray astronomer that looks at the X-ray data, comes up with some conclusions, and talks to the infrared astronomer and compare the results. But that is like if you were taking a picture of this room from one side and then another one was taking a picture from another perspective, and then you have to talk to each other to figure out how the room looks. So now with AI, that's one of the things that we can do is process data from different types, different modalities together, and access finally patterns in a higher dimensional space. So as humans, we're limited to a three-dimensional space for visualization, and if you have many telescopes looking at the same phenomena, you want to take advantage of these correlations and these patterns that are in high, in high dimensional space. And if I can give you a quick example of that, is in the theme that I've been talking about today, we have the Chandra X-ray Observatory. That's one of the great observatories from NASA looking at the world in X-ray, at the universe in X-rays, so very high energetic phenomena. Chandra has measured the X-ray emission of hundreds of thousands of stars, and that is very important for habitability. Because if a planet is close to a star that is very magnetically active, that can actually strip their atmosphere, evaporate it. Well, that's what we think happened to Mars. The solar wind, pushed by these magnetic fields, strip the atmosphere. And so if we can find the correlation between the X-ray measurement, that we can look at X-rays much further, and it's much cheaper, and we have a lot of them, and the signatures in the atmospheres of the planets that we only have for a few, like 10, 20 or so, then we can unlock this discovers much further, and we can understand what planets are likely to have life from a lot more observations that we have available already.
Thanks. I have 2 minutes, so I want to ask the same question to both of you, forward-looking question. In 10 years' time, what discovery made possible by AI do you think will change how we understand our place in the universe?
Well, I have to say finding life elsewhere in the universe is my favorite one, that if you haven't noticed it so far. No, I do think that unlocking that is going to change completely how we think about ourselves as civilization.
Dan?
Well, so because there isn't a particular, we're going to have much greater fluency with what's happening on the Earth's surface, and the maps will be denser. You know, when you go to Google Maps right now, you'll see big blank spaces, questions that you can't answer, and you'll be able to answer them. As we've seen, one of the biggest, the biggest geographic information system platform out there really is Google Maps. I mean, that's something like 10 times the annual revenue of the next biggest GIS tool out there. But we don't even recognize it. It's just sort of like part of the fabric of the way in which we go about our daily lives. Most of that came from advertising as a result, or it is because of advertising as opposed to tooling. But we don't even notice it. And I think that's probably true for Earth observation. It will have to be an ingredient. It won't be sort of the end. You won't be able to track a whole decision all the way through Earth observation. That's never happened. It's always been used in conjunction with other sorts of analysis. And I think that's true in this sort of AI-first space also.
Thank you. It's an exciting time for the planet, exciting time for the universe. Thank you to both our presenters, panelists. Thank you to the audience.
Thanks.